Hello, I'm Chris Barclay, the product manager for Wavelength. Thank you for joining me to discuss how Wavelength enables developers to deliver applications that require ultra-low latency to users and devices on 5G mobile networks. In today's session, I'll describe why we built Wavelength, use cases for why developers are using Wavelength, and dive deeper into the developer experience. Before getting into what Wavelength is, let's delve into the technology trends that are ushering in new use cases that would not have been possible to deliver with LTE cellular technology. 5G technology delivers benefits such as ultra-low latency and high bandwidth, and in the future, network slicing to carve out bandwidth from the physical network for applications. This enables new use cases like cloud streaming and AR/VR, where even differences of tens of milliseconds can hamper the end user's experience. These new use cases are driving not only the demand for edge computing, but new requirements on where data is processed, analyzed, and sent to the end user to make informed decisions in real time. Over the coming years, there will be billions of devices such as IoT sensors and video cameras that will generate petabytes of data. For example, smart factory industrial automation applications use ML inference at the edge to analyze videos to detect quality issues on fast-moving assembly lines and trigger actions to remediate problems. In order to be responsive, the processing of latency-critical data needs to happen at the edge. Customers expect 5 core values from mobile edge infrastructure. First, they need ultra-low latency to enable real-time, immersive experiences for their end customers. Second, they want to be able to get access to compute and storage without capital expenses and be able to scale up and down elastically with pay-as-you-go pricing. Third, they want to be able to deploy the same application everywhere, irrespective of where the app is hosted, whether it's in the cloud, or on the edge, or across various telecommunications carriers, with well-known AWS services. Fourth, they want to manage their application using the same tools as they're used to. And last, they want access to the same features at the same fast frequency of delivery that they're used to in the cloud. Now that we've discussed some of the technology trends, let's discuss AWS offerings at the edge. AWS has dozens of regions that enable developers to build applications that provide low latency globally and a comprehensive set of solutions for building edge applications. Outposts, local zones, and Wavelength all bring AWS services to more places with the same experience and benefits that developers are used to. Wavelength, however, is unique in that it is designed to enable developers to build ultra-low latency applications by extending AWS services into 5G mobile networks. Developers can take existing applications and extend them to Wavelength zones, or build new applications using AWS services like EC2 and EKS. Wavelength is AWS infrastructure that is located and installed in a physical site that is part of a communications service provider network. A communications service provider network has physical locations, such as cell towers, that connect with traffic aggregation points at metro levels. Wavelength zones are installed in these metro aggregation sites. The 5G access network is directly connected to the Wavelength zone through a construct called the carrier gateway, allowing mobile devices to access the instances in a Wavelength zone without going to the internet. Wavelength zones are managed and monitored by AWS and connected over a highly reliable link to the AWS region. Applications in Wavelength zones can use core services such as Amazon EC2, EBS, ECS, and EKS. Applications can also connect seamlessly to other services such as DynamoDB and S3 in the same AWS region. You can deploy portions of your application requiring ultra-low latency to Wavelength and then connect seamlessly to the rest of your application and services running in AWS regions. Wavelength zones deliver a consistent developer experience across multiple 5G networks around the world. Wavelength is available in several locations in North America with Verizon, with plans to launch in Europe, Japan, and South Korea. So why should you care about low latency access to compute? We all encounter examples of latency in our daily lives. And even when there's lots of bandwidth, the number of hops or the distance traveled matters. To solve these problems, developers told us they wanted to bring the cloud to the device. We saw an opportunity to combine the benefits developers have come to love about the AWS cloud, including a broad set of services, pay-as-you-go pricing, and elasticity, with the ultra-low latencies and high bandwidth of 5G, to enable developers to create truly novel experiences. Wavelength brings AWS services to the edge of the 5G network, minimizing the latency to connect to an application from a mobile device. Emerging interactive applications like game streaming and virtual reality require ultra-low latencies to end users and devices and consistent quality of service on data flows to deliver the desired experience. The 5G network is up to 20 times faster than 4G and can be used to shrink network latency. However, even with the arrival of 5G, mobile devices still had to cross multiple network hops when connecting to an application over the internet. Before Wavelength, application traffic had to travel from a device to a cell tower to a metro aggregation site and then onto the internet before it could reach resources running in AWS. These network hops could result in latencies of tens of additional milliseconds. Previously, this prevented developers from realizing the full potential of 5G to address low latency use cases. One class of applications with these requirements is inference at the edge, such as a smart factory where sensors can detect quality problems, and healthcare for doctor assistance during procedures. One challenge with machine learning applications is system responsiveness, which requires the inference processing application to be close to the end user. This used to mean the device needed expensive and power-hungry processors. Additionally, if you needed to update your machine learning model, you had to push out an update to all the devices running your application. Now, 5G and Wavelength provide significantly lower latency and much more bandwidth compared to previous generation mobile networks, allowing you to use the cloud as an extension of your mobile device. For edge applications, this implies you can actually perform inference processing, even with HD video, in a wavelength zone with real-time responsiveness to the mobile device. By moving the inference processing to the wavelength zone, you reduce power consumption and battery drain on the mobile device. And additionally, you can simplify application updates. If you need to make a change to your training model, you simply update your servers in the wavelength zone instead of having to ship out a new version to all the devices running your code. There are many use cases where Wavelength can help, including healthcare, where AI/ML-driven video analytics and image matching solutions can help doctors speed up diagnosis of observed conditions, such as recognizing polyps during colonoscopies. The video streams from medical devices are processed in a wavelength zone, and the response is returned to the medical device for the surgeon to use. Connected cars enable capabilities such as improved road safety. Low latency access to compute infrastructure is needed to run data processing and analytics to monitor data from sensors for secure connectivity, in-car telematics, and safety warnings. Wavelength also provides the ultra-low latency needed to live stream high-resolution video and high-fidelity audio, as well as embed interactive experiences into live video streams. Additionally, video analytics provide the ability to generate real-time statistics that can enhance live event experiences. Wavelength provides 4 benefits. First, Wavelength brings AWS services to the edge of the 5G network, minimizing the latency to connect to an application from a mobile device. Application traffic can reach application servers running in Wavelength without leaving the mobile network. This prevents the latency that would result from multiple hops to the internet and enables customers to take full advantage of the advancements of 5G. Customers can now deliver immersive experiences like game streaming to end users on mobile devices. Robots, cars, and other smart devices can make complex decisions that require more computing power than is available in a small form factor. Bringing AWS closer to end users and devices unlocks these new opportunities. Second, you deploy your application to wavelength zones. AWS infrastructure and deployments that embed AWS compute and storage services within telecommunication providers' data centers at the edge of the 5G network. Wavelength zones deliver a consistent developer experience across multiple 5G networks around the world, allowing you to build ultra-low latency applications using the same familiar AWS services, APIs, tools, and functionality you already use today. You can deploy portions of your cloud-based applications requiring ultra-low latency to Wavelength, and then connect seamlessly to the rest of your application and services running in AWS. Third, with Wavelength, you get capacity close to your end users and data, along with AWS benefits such as no capital costs, pay-as-you-go pricing, and the ability to scale up and down on demand. Finally, AWS regions, local zones, and wavelength expand AWS to deliver ultra-low latency to more locations around the world. You get these same benefits whether end users connect over the internet or mobile networks, in the Americas, Europe, Japan, Korea, and more locations to come. So how does Wavelength deliver these benefits? Unlike previous generations of mobile networks, which were just about increasing bandwidth, 5G is about a lot more. 5G provides benefits of more bandwidth and lower latency from the mobile device to the compute running in the wavelength zone. It achieves this through advances in wireless technologies. Upper bands of the spectrum are being used to deliver higher bandwidth. Wider spectrum band equates to higher bandwidth. Then, new antenna technology is being developed that supports more mobile devices at high bandwidth. And later, network functions will enable the network to be virtualized, providing flexibility of deploying components in various parts of the network and dynamically adjusting the network for what each component needs. The latency of applications deployed to AWS regions depends on where the users are, where the regions are, and the specific paths traversed to each of the applications from the regions. The latency typically is on the order of tens of milliseconds if you look across a broad population of mobile users. With compute instances running at a site embedded in the mobile network, this distance is reduced. And since the network path traversed is shorter and the quality of service is highly controlled in a mobile network, the latency is predictable and has less jitter, which is important for applications such as gaming and others that require tight synchronization across users. In addition, use cases with high data transfer can process it earlier in the network path, reducing the bandwidth used in backhaul networks. Now that we've described why we built Wavelength, let's dive a little deeper into the developer experience. Wavelength is built with familiar AWS services and offers Amazon EC2 instances featuring Intel Xeon scalable processors. In addition to EC2 instances, you can use EBS for application storage and use Amazon ECS and EKS for your containerized applications. Amazon EC2 instances and Wavelength are powered by Intel technologies, offering consistent application performance and the ability to run the same application across AWS regions and Wavelength zones. If you're already running your applications on Intel Xeon-based instances in the AWS region, you'll enjoy the same benefits at the edge, including software optimizations to improve application performance. Let's look at some of the concepts of wavelength zones that we can see from the Describe Availability Zones API. First, you need to be opted into Wavelength to use it. The zone name is passed into APIs like Create Subnet, just like availability zones are today. The group name is used to refer to groups of wavelength zones for a particular carrier. This group is Verizon zones in the Northern Virginia region. You can also see the network border group, which you use to allocate IP addresses on the carrier's network to elastic IPs used with the EC2 instances. Applications built on Wavelength start with a VPC, just like you use for applications on AWS today. Wavelength zones use existing availability zone concepts. After you create a VPC, you create subnets in a wavelength zone, along with route tables, security groups, and other resources as you're familiar with. EC2 instances and wavelength zones are created in a subnet in the VPC and use the VPC's IP address range. This enables your application components in wavelength zones to use a secure and high bandwidth connection to access all of the resources in the region. And then you can create a subnet in the wavelength zone just like other subnets, where you specify the VPC and the CIDR range for the subnet. In this example, you can see that instance Y in the wavelength zone can connect to instances B, D, and Z over the local VPC network. Existing concepts like transit gateways and VPC peering continue to work, and you can use endpoints for services like S3. With Wavelength, we've introduced a carrier gateway to route the traffic between the wavelength zone and the carrier network in a specific location, as well as outbound traffic to the internet. The carrier gateway provides connectivity between your wavelength zone and the telecommunication carrier's network, including mobile devices on that network. The carrier gateway performs NAT for the EC2 instance's private IP addresses to the carrier IP addresses from a pool that's assigned to the network border group. The carrier gateway NAT function is similar to how Internet Gateway functions in the AWS region today. Now that we've described how Wavelength uses the same VPC constructs as you're used to in regions, let's describe how data flows from EC2 instances and Wavelength zones. EC2 instances and subnets in Wavelength zones can connect to EC2 instances and subnets in availability zones over a high availability link using the private IP addresses in the VPC. This makes it incredibly easy to have some parts of your application run in the region and other parts run in the Wavelength zones. In addition to private IP addresses in the VPC, you can put a carrier IP address on each EC2 instance. The carrier IP address is on the carrier's network in the specific location. For example, in the Boston Wavelength Zone, it is on Verizon's network in Boston. Connectivity to the mobile network goes through the carrier gateway, allowing a device in the carrier network to connect to the EC2 instance, subject to your security group rules. The carrier gateway also provides egress to the internet, so you can connect to the internet resources like GitHub or to get operating system updates. Note that this path is for internet egress and response. Wavelength zones are not accessible from the internet. Now that we've described how the Wavelength network works, we'll discuss edge application architectures. When you're constructing applications, you need to consider the processes and the call path from the end user. Wavelength zones are designed for applications that need to connect to compute from devices on 5G networks with ultra-low latency, as well as applications that need high and consistent data rates from devices on 5G networks. AWS recommends you architect the edge applications in a hub-and-spoke model, with the region providing the most scalable, resilient, and cost-effective options for components. You can run the application components that are less latency sensitive or that need to persist data, such as databases, training ML models, and back-end worker processes in the region. You then run applications components that are latency sensitive in the Wavelength zones. In a hub-and-spoke model, the hub is in the region and the spokes are your edge locations. In addition to Wavelength zones, edge locations can also include local zones, outposts, and even regions. Let's put this all together to see an actual example of a customer application deployment. A gaming application typically has a game server that runs the game session and does a lot of the real-time video rendering. These are latency sensitive. Then there are services that maintain the state of the player, which might need to be recovered if the game is paused, and these are not latency sensitive. And there's the game image that's typically stored in S3 in AWS regions. In such a scenario, the developer would determine where the end users are geographically and decide on where they want to deploy the game servers. This could be in one or more Wavelength zones, for example. The developer would create a VPC and launch the game server in the Wavelength zone and deploy the state service in a region. The image download would happen from S3. Now with the game server running in the Wavelength zone, a mobile device requesting to use this would first reach a service discovery service in the region. And this service discovery would know where all the instances of the game servers running across the Wavelength zones are and would determine which one would be the best for the end user to connect to. The device would then connect to the application over the 5G network through the carrier gateway. So as you can see, Wavelength zones provide compute at the edge with the developer experience the same as in AWS regions, but you're still using the same EC2 instances and VPCs, and at the same time this gives you the flexibility to construct your applications that use 5G networks and with regions. So in this example, the latency-sensitive portion of the application, the game server, is placed in the Wavelength zone, while the non-latency sensitive components like the player state service and the matchmaking service are placed in the region. Putting this hub-and-spoke model into practice, you can create infrastructure as code templates, for example, using a service like CloudFormation, for hub resources like VPCs and S3 buckets, and spoke templates for resources that are deployed at every edge location such as subnets and autoscaling groups. You can then use CloudFormation to provision the resources consistently across locations. CloudFormation supports parameters to let you customize attributes such as AMI IDs or subnet CIDRs that may change between edge locations. Once you've provisioned the hub template, you can provision your spoke templates. Spoke templates typically reference resources in the hub template. For example, a subnet needs to reference a VPC. You may have an EKS cluster provisioned in your hub template, and autoscaling groups for EKS node groups provisioned in your spoke template. Of course, while tools like CloudFormation ensure consistency and allow you to treat configuration as code, manually provisioning, even from templates, can be time-consuming as the number of locations increases. And this calls for more automation. Instead of calling CloudFormation manually, you can use a deployment tool like CodePipeline. CodePipeline allows you to break up a deployment into stages. Each stage can have one or more actions. For example, you probably want to connect the pipeline to your source repository like GitHub. When the configuration changes, the pipeline will initiate its workflow. The first stage might be to deploy to the Northern Virginia region. In this stage, you'll have multiple actions. The first action is to use CloudFormation to provision your hub resources. The second action might be to use CloudFormation to provision your spoke resources in the Boston Wavelength Zone. The third action might be to use CloudFormation to provision the spoke resources in the New York City Wavelength Zone, and so on. The second stage might be to deploy to the Oregon region. Using a method like this enables you to deploy safely and consistently to a growing number of edge locations. Now, once you have your application deployed to the edge, how do client devices find the lowest latency connection to connect with? Latency-based DNS routing works well over the internet. But over a mobile network, latency-based DNS will return the nearest location of the resolver, which may or may not be the closest edge location. What we want is for the device to connect with the resources in the closest edge location, such as the resources you've just provisioned in your wavelength zone. This requires two steps. First, you register your application resources in a registry and annotate those with metadata to describe what zone they're in, as well as geolocation for the zone. You can use a service like AWS Cloud Map to register the endpoints. Here we show creating a service in Cloud Map for your application, and then registering particular instances that you've put into wavelength zones, along with the metadata, such as the lat/lon, the zone name, and as well as other metadata like your production version of the application. The next step is to use the geolocation of the device to determine where it is. From there, you can find the endpoints that are geographically closest. For example, the latitude of Atlanta is 33.75 and the longitude is minus 84.38, while the latitude of New York City is 40.73 and the longitude is minus 73.93. So you can easily find what's closest to the geolocation returned from the client device. And then you can use APIs to find out what network the device is on, or use a ping test to identify the closest resource to connect with. Then you can connect with the closest endpoint. Now, mobile devices could be on mobile networks, or they could also be on Wi-Fi. And this process works the same whether the device is on that mobile network or Wi-Fi. Simply use the ping test or identify what network the device is on, and you can make the right connection. So now I've explained how to architect your application into hub and spoke components, how to provision those components in an automated way to the edge, and how to locate the best resource from client devices. Thank you for coming to the session today. Again, I'm Chris Barclay, the product manager for Wavelength. I appreciate you coming to hear about Wavelength, and please check us out on aws.amazon.com/wavelength to learn more and try it out.